Okay. Sorry, it took me a while to get that arranged. To slideshow, we're going to go over the quiz from this week. Well, I guess we'll just have to work from here. Okay. So, first question. First of all, y'all did pretty well on this. I'm really happy. If you're not understanding it after going through this with me, please just let me know and or the tutors know and maybe even make a special appointment to make sure you have all of these um, concepts really strong for the exams, renal and hepatic clearance, okay? All right. So VH is an 18-year-old female who was in a motor vehicle accident. She's in acute renal failure post-trauma. She's 5'7" and weighs 150 pounds. Her serum creatinine is 3.5 milligrams per deciliter. So she's got some renal impairment. Her albumin is decreased. So if her albumin is decreased and her AAG is increased, so we expect some fraction unbound changes, right? We expect some protein binding changes due to the renal failure trauma. She's on the following drugs. Which of these drugs would you expect an increase in clearance if an osmotic diuretic was added? Well, let's talk about that first. So if an osmotic diuretic were added, what does that do? That will decrease tubular reabsorption of water. Therefore, the things in the tubule will not get as concentrated. Therefore, you're going to decrease renal reabsorption, aren't you? Because that's a passive process that's dependent upon that concentration gradient. And if you don't have the drug, in this case, in the tubule being concentrated as it goes down as much as it would, you would decrease the reabsorption that happens. So if you decrease reabsorption, it's staying in the tubule and you'll have, when it wouldn't have been before, and you'll have an increase in your renal clearance. So what we're looking for is any drug, doesn't matter whether it's an acid or a base, any drug that undergoes predominantly reabsorption, passive reabsorption. So we're looking for all drugs that are predominantly reabsorbed. So now we have to go through all four of these drugs and determine their glomerular filtration clearance and their renal clearance and their predominant processes. And then we can use that for the rest of the questions in the quiz, so it won't be wasted time at all. So to determine the glomerular filtration clearance, we are going to figure out what the GFR, which normally is 125 mils per minute, or 7.5 liters per hour. We're all in mils per minute here, so we'll do 125 mils per minute times whatever the fraction unbound is, because remember, only free drug is cleared. So glomerular filtration rate is 125 mils per minute. So for ceftazidime, it's going to be 125 mils per minute times what's unbound, which is 0.9. So it's very highly unbound, not very highly bound. So this is going to be 112.5 mils per minute. And for gentamicin, it's 125 times 0.95, even more highly unbound. So that's going to be 118.75 mils per minute. And this is all in mils per minute, because we want to make sure that we're comparing apples to apples. So we're going to need to make sure our renal clearance is in mils per minute, aren't we? Okay, phenytoin is only 0.1% bound, so it's going to be 125 times 0.1 or 12.5. We don't really need a calculator for that one, do we? And then finally, furosemide, which is only 5% free, so it's highly bound, isn't it? So 0.05 times 125, 6.25. So this is what's coming into the nephron. So 112.5 mils per minute is coming in, 118, 12 and a half, and 6.25 mils per minute is coming into the glomerulus being filtered in. So now we're going to compare what's going out. And so in order to do that, we have to figure out our renal clearance is going to be our total body clearance times the fraction that it's excreted unchanged in the urine, right? So what percentage shows up in the urine? So again, our clearance luckily is in mils per minute, so we can go with that. So we've got total body clearance is 150 for ceftazidime. So it's 150 times 0.9. It's very highly cleared most all by the kidneys. So 135 mils per minute. And gentamicin is 120 mils per minute, and it is 0.95% cleared by the kidneys, so this is 114. And then phenytoin is 0, so none of it's being eliminated by the kidneys. And then 0.9, 90% of furosemide is, so 0.9 times 150, so it's 135, just like ceftazidime. All right, so if we have, let's look at ceftazidime. 112.5 mils per minute is coming into the glomerulus, and 135 is coming out. So it must be predominantly secreted because drug is added right before from the filtration. So we have more drug going out than came into the tubule. So we must have a predominantly secretion, active secretion going on. How about gentamicin? We have 118 coming into the tubule and 114 going out. So we have a little bit of reabsorption going back into the body, right? Because 100, almost 119 coming in and 114 going out, it's being reabsorbed. 112 going in, 0 going out, so again, being reabsorbed. But considering there's really no renal clearance at all with phenytoin, this is probably all moot. And then finally, with furosemide, we have 6.25 coming in, but 135. So there's a lot being added here, right? So we have 6.25 coming into the I'm sorry, coming into the tubule, and 135. So there's a lot being secreted. And this reabsorption is really well, I guess we could give credit for phenytoin, but really there's no renal clearance there. So it really should be ceftazidime and maybe phenytoin, but ceftazidime is, wait a minute, what are we looking for here? Which of these drugs? So the only one is gentamicin, right? Gentamicin. It's reabsorbed. Gentamicin and maybe phenytoin. So that's the answer if an osmotic diuretic were added. So it's going to be gent and maybe phenytoin. I'll give credit for both. Okay, good. Now we've got all the hard work done. We're going to go on to the next one. Maybe. Wait, I've got to get rid of all of this first. Well, maybe I don't want to do that. I'm going to just keep moving. Oh, but I don't want it staying on the screen, do I? Okay. So we have to remember secreted, reabsorbed, reabsorbed, secreted. Okay. Mm-mm-mm. All right. Which of these drugs would you expect? So we're going to do, let me just write this on here. Secreted, reabsorbed, reabsorbed, maybe. Secreted. Okay, so which of these drugs would you expect a decrease in clearance if a drug that alkalinizes the urine is added? Again, this will only concern reabsorbed drugs. So reabsorbed drugs, so a decrease in clearance would be caused, a decrease in clearance would be caused by what? We know changes in pH of the urine is only going to affect reabsorbed drugs. And therefore, to decrease the clearance, you're going to have to increase reabsorption. So how do we increase reabsorption? We have the drug more in the unionized form, right? Unionized form. So what kind of drugs are going to be more in the unionized form if we alkalinize the urine? So alkalinizing the urine is an increase in pH. So an acid is going to be more in the ionized form. That's going to increase clearance, but a base is going to be more in the unionized form, which is going to favor reabsorption and therefore decrease clearance. So we're looking for a drug that's primarily reabsorbed that's a base. So that's going to be gentamicin, isn't it? Good. We're going to go to the next one. Which one of these drugs would you expect a decrease in clearance if a weak base is added that is cleared by the kidneys, primarily secreted, and is a weak base? So let's take each of those step by step. Okay. So which of these drugs would affect a decrease in clearance if a weak base is added that is cleared by the kidneys, primarily secreted, and is a weak base? Okay, so we have a weak base that's primarily secreted. So we're going to only be looking for our secreted drugs, which are these two, right? Because these are both reabsorbed. So we're going to be focused on ceftazidime and furosemide. If a weak base is added, so the only drugs that a base would be competing with a base. So in this case, it's ceftazidime, right? So let's make sure that happens. So if a weak base with a relatively low KTS, so that's going to mean that it has a higher affinity, right? And therefore it will displace our drug that we're taking already to get that ride into the urine. So we'd have a decrease in clearance of our ceftazidime, wouldn't we? So the answer here is a decrease, is ceftazidime. Ceftazidime, because it's secreted and it's a base, would be competing with this new primarily secreted drug that's a base. And this base has a lower KTS. So this base is going to be preferred to use that carrier taking the drug from the blood into the urine, and therefore our drug ceftazidime will be left in the blood because it isn't going to get the ride into the urine, and therefore the clearance is going to decrease. Okay, good. All right, next one. I think this is the last of our, I have to get rid of that. The last of our questions, I think, about patient VH. Okay, so VH, which of these drugs would you be least likely to need to change the dosing regimen based upon her renal impairment? All right, she has renal impairment. We know that because of the 3.5 milligrams per liter of her creatinine, and we didn't even figure out her actual creatinine clearance yet. I don't know, maybe we're asked to do that. We should be able to do that though, right? So which ones are we going to be least likely? Well, we're going to look at, well, what organs is this drug dependent upon for clearance? Well, furosemide, gentamicin, and ceftazidime are 90% or more dependent upon the kidneys. So these are the ones we're most worried about. Phenytoin doesn't depend on the kidney at all to clear the parent drug of phenytoin. So this answer would be phenytoin. See? Yeah, we're done with those now. Okay. So a new drug, gravaricol, is under development and has just undergone phase 1 trials to determine the human pharmacokinetics. The studies have obtained the following information. First of all, total body clearance is 1,000 mils per minute. It's 90% cleared by the kidneys. It's 75% free from protein binding, and it's got a volume of 2.5 liters per kilogram. So it's a relatively large volume of distribution, and it's a weak acid. So which of the following would affect the clearance of the drug? Okay, so let's figure out how this drug is mostly cleared by the kidney. So it's the renal clearance is going to be 900 mils per minute. We can do that without a calculator. How about our glomerular filtration clearance? Well, we're in mils per minute, so 125 mils per minute times the fraction unbound, which is 0.75. Sadly, I think I do need a calculator for that. So filtration clearance is going to be 93.75 mils per minute. So what's coming into the nephron is 93 mils per minute, but what's going out is 900 mils per minute. So we have a lot of secretion, right? So this is active secretion. So which is going to affect the clearance? Well, it's going to have to be a drug that's primarily secreted, but remember, it's the secretion carrier sites are specific to whether it's a weak acid or a weak base. So it's going to be drugs that are predominantly secreted and an acid. So that's this one here, right? So it's not going to be all drugs predominantly reabsorbed. It's not going to be all drugs predominantly secreted because it depends on whether it's an acid or a base. We can get rid of these reabsorbed and just focus on these secreted. And we know since it's an acid, it's going to be competing with another acid. Okay? And then we would want to see their relative KTSs to see which one would win that ride into the urine. All right. Drug K has an Fe of 0. What does Fe of 0 mean? Well, that means that none of the clearance is dependent upon the kidneys. So really here it's a hepatically cleared drug, we're assuming. So Fe is 0, fraction unbound is 0.14, so it's highly protein bound, is cleared by the kidneys. Is that true or false? No, it's false, right? Because it's we just said if there's no drug found in the urine that's still of the parent drug, we know that it's all being metabolized or cleared in another way. Okay, next one. Which of the following statements about tubular reabsorption is false? This is a tricky one. It's probably not a good way to ask the question, so I apologize. But let's think about this. So we're looking at tubular reabsorption. So we know this is a passive process, and the drug has to be unionized, has to be small. There has to be a concentration gradient, right? So, and it has to be lipophilic enough to pass through that membrane to get reabsorbed. So tubular reabsorption depends on the pH of the urine. Yes, that's true, isn't it? Because the ionization character matters. Highly ionized drugs tend to remain in the urine and not be reabsorbed. That's true too, because it can't pass through the membrane to get reabsorbed. Tubular reabsorption can only be achieved by an active transport process. This is false because it's a passive process, right? There is some tubular reabsorption that is active, but that's not the usual process for drugs. So this is probably our answer. Let's read our last one to be sure. Tubular reabsorption is dependent upon concentration gradient. Yes, that is true as well. So this one is C, isn't it? I hope that was an easy one for you. All right, a normal creatinine clearance is 125 mils per minute. However, your patient's creatinine clearance is only 33. So what is your patient's renal function? So we know that's going to be less than 0.33. Round it to your nearest hundredth. All right, I think one or two of you did not put this in the 0 to 1 format, but put it in a percentage. Be careful about that if I ask you. Renal function should be between 0 and 1. So 33 divided by 125. So I got 0.264, and we're going to round to the nearest hundredth. So we're going to say 0.26. Okie dokie. If the renal clearance is greater than the filtration clearance, you know the drug is primarily, okay, so again, the way you want to think about this, so what's coming into the tubule through the glomerulus, here's our nephron, here's our blood surrounding, so this is urine. So we have drug coming in through glomerular filtration. So if what's going out is greater than what came in, we had to have drug added, didn't we? So that's secretion, isn't it? So we had to have predominantly secreted. For reabsorption, the renal clearance will be less than what was filtered, right? And all drugs are filtered, so both reabsorbed and secreted drugs will be filtered. And it could be that both reabsorption and secretion is happening, but we know for sure that if the renal clearance is greater than filtration clearance, that secretion is occurring. And I think this is our last question, which should have been a very easy one. Name the two processes in renal clearance of drugs that add drug to the nephron. I think almost all of you got this. So remember, we have three processes. We have filtration, and all drugs are filtered. This is blood that's coming through the glomerulus into the nephron. And again, if we have our blood here, right? And then our bladder down here, eventually we get down here to the bladder and out of the body, right? So we have filtration, and then we also have drug actively moving from the blood into the nephron, which is called active secretion. Both of those are adding drug to the nephron, aren't they? And then finally, after we have significant water reabsorption, and the drug becomes more and more concentrated as it gets down here, we have passive tubular secretion, or I'm sorry, tubular reabsorption. And that reabsorption is a passive process for the most part, and it takes drug back out of the nephron. So it doesn't add drug to the nephron, but it takes it out. So your answers are filtration and active secretion. Great. Most of you did very well. If you didn't, I hope this helps. So we're all done. Thank you very much. Bye.